Hey everyone, welcome to this explainer brought to you by Forge College. Now, if you've been following along with us in the Applied Solidity Development track, specifically our module on designing smart wallet patterns, you'll remember our previous lesson on scoping the decision framework. In that one, we mapped out our integrated smart wallet, defined the public entry points, and set up our integration milestones. But, mapping the terrain is really only half the battle. Today, we are diving deep into the engineering blueprint for truly securing that wallet. We are officially moving from the planning phase into the proving phase.
So it's the million-dollar question. And honestly, in Web3, sometimes that is quite literally $1 million. You have a plan, but how do you actually prove it works? I want you to think of your smart wallet like a highly secure physical bank vault. You've designed these massive fixed steel walls, you've picked out the complex time locks, and you've set up a state-of-the-art alarm system. But you would never actually deposit real hard-earned funds into that vault without subjecting it to some rigorous, punishing stress tests first, right? We have to verify that our code acts exactly as intended when it's under intense pressure.
Okay, let's dive right into this. Here's the schematic blueprint of the checkpoints we'll be clearing today. First, the testing reality check. Then, our 3 layers of defense, mocking the outside world, looking at code in the trenches, and finally, automated security guards.
All right, kicking things off with Phase 1, the testing reality check. This is where we take things from abstract to concrete.
This is the moment we transition from those lofty abstract plans into hard, verifiable code. Our integration milestones give us what we call acceptance criteria. You can think of these as totally concrete behavioral checkpoints. So instead of a vague goal like, hey, let's make the wallet secure, an acceptance criterion is incredibly specific. It's something like, owner rotation succeeds only when executed by a 2 of 3 multi-sig guard. These are the exact, non-negotiable targets our test literally must hit to prove the vault is secure. If a test doesn't pass, the criterion isn't met, and that vault stays empty.
But here's a little reality check within our reality check. Aiming for 100% test coverage across your entire codebase, that is often a total illusion, and frankly, it's kind of a waste of time if you're just testing trivial getters. Instead, we use what are called coverage thresholds. These are explicit, measurable goals that stop us from falling into the endless trap of just writing tests for the sake of writing tests. By setting smart thresholds, we focus our absolute maximum effort exactly where the risk is highest. We're talking those critical areas like upgrade paths, signature validation, and owner management.
Moving on to Phase 2, 3 layers of defense, and how we actually structure these tests. So we can't just throw tests at the wall and hope something sticks. Think of our defense structure like this. Our very first layer is unit tests. These are lightning fast, taking mere milliseconds to run. It's basically the equivalent of checking if the vault door hinges are properly oiled and if the individual gears inside the lock actually turn. You're testing single functions in total isolation, like basic signature validation. Then, we step things up to integration tests. These take a few seconds. Now we are checking if the wallet contract correctly interacts with a relayer and an ERC20 token. It's like testing if the vault door actually locks when the alarm system sends it a signal. And finally, we have end-to-end, or E2E tests. Now these can take minutes. This is where you literally hire a team of mock bank robbers to try and execute a full-blown heist. You're testing the complete user journey, from deploying the wallet all the way to onboarding an owner and executing a meta transaction.
Now, what's really interesting about this slide is how we actually apply our coverage thresholds here. Instead of just giving developers a vague mandate to test everything, we set highly pragmatic, targeted goals. For instance, we might demand exactly 90% coverage on non-trivial code paths specifically within the signature and wallet modules. Make sense? We are prioritizing the core armor of our vault, rather than spending all our time testing the decorative lobby.
All right, let's look at Phase 3, mocking the outside world and controlling our sandbox.
So what actually happens when our smart wallet needs to interact with completely unpredictable outside forces, things like off-chain relayers or those notoriously flaky Oracle feeds? Well, we definitely can't rely on the actual live networks during our testing. They are way too slow and honestly just too unreliable. And that brings us to mocking. When we are testing features like gasless transactions with off-chain replay protection, we need total, absolute control over the environment. So we fake it. First, we identify the off-chain service, let's say a relayer. Second, we build a mock or a stub of that exact service right within our own test environment. Third, and I think this is the really fun part, we simulate extreme edge cases. Because we completely control the mock, we can intentionally bombard our wallet with duplicate messages or simulate massive network latency just to guarantee our replay nonce logic holds up under absolute chaos.
Which brings us to Phase 4, code in the trenches. utilizing hardhat and ethers.js.
Okay, let's pull back the curtain for a second and look at how this actually translates into your code. Just imagine a test file that maps directly to our acceptance criteria for meta-transactions. First things first, before every single test, we set up our accounts. We're talking an owner, some random other user, and a relayer with a completely fresh state. Next, we write a unit test for signature recovery. We use call static so the EVM returns the recovered signer address without actually making any changes to the blockchain state. Then we move right into an integration block. The owner signs a payload to transfer tokens, but, and this is key, the relayer is the one who actually calls execute meta task on the wallet. Finally, we just assert that the token transfer event fires correctly and that the balance is update. This logic, going block by block, mathematically proves that an intermediary can safely execute a signed payload on behalf of the actual owner.
Let's move to phase 5 and see how this all builds together with automated security guards and continuous integration. Look, running tests manually on your laptop is great, but let's be real. It's not scalable, and human memory is deeply flawed. We forget things. This is where continuous integration, or CI, steps in. I like to think of a CI pipeline as a team of automated security guards standing right at the door of your main code repository. Step 1. You do a super fast local run of your unit tests. Step 2. You push your code to a pull request. Step 3. The CI pipeline automatically spins up and runs those slower, much heavier integration and end-to-end tests in the background. Step 4. The guards make a decision. If even a single unit or integration test fails, the merge is blocked. Period. No exceptions. Now, if an E2E test shows some flakiness, it gets logged as a defect for triage. Your code only merges to main when it definitively proves its worth.
So the absolutely crucial point here is this. None of this beautiful structure works if you don't actually know why a test exists in the first place. You must always annotate your tests with their corresponding milestone IDs. It's super simple. Just drop a header comment in the test file, linking it right back to your project plan. When a reviewer looks at your code, they shouldn't have to play a guessing game about what a test is doing. They should be able to instantly audit your test coverage against the exact acceptance criteria we defined way back in the planning phase.
And I think this brilliantly illustrates our final takeaway for today. Tests are a living contract between your implementation and your acceptance criteria. They're not just chores you have to check off a list. They are the literal executable proof that your smart wallet does exactly what it promises, safely and reliably. By layering your tests, setting those smart coverage thresholds, and automating the gates, you are building a highly defensible safety net for your capstone project. But I want to leave you with this question. What hidden vulnerabilities are lurking in your codebase right now, just waiting for a missing test to let a hacker slip right in? Thank you so much for joining me for this explainer. To learn how to find those vulnerabilities and explore a whole lot more about this subject and other Web3 related topics, please go ahead and visit the website forge.college. Keep building, keep testing, and I'll see you all next time.